Okay, law of total probability. This is very much important in Bayes' rule, which I'll write in a second. So that dot simply means, there's a whole bunch of partitions. So this is a case where we'll call that B. The set B is the B that's a rectangle, and B is formed using partitions A1, A2, A3, all the way up to AN. The partitions are disjoint of each other. In a sense, there is no overlap. The intersection of all of them would be empty. If that is the case, is there a way to write B, the event B, in terms of A1, A2, all the way up to AN? So I want to express B using A1, A2, A3, AN. And then there's, of course, the outer big set. What do we say?
It would be the union of, it would be like from I equals 1 up to N of A sub I.
Like the union of all intersects. That's what I'm going with. So I could use the case, I could write it as B intersect A1. Yes. Just to write in a different way. Union B intersect A2. Union B intersect A3. Dot, all the way up to B intersect AN. Right? Clearly, these would be disjoint also because A1, A2, all the way up to AN, they're all disjoint. If they are disjoint, then these events are disjoint also, so we don't have to worry about putting other things together. So the probability of B would simply be the sum of all of those probabilities because they're all not independent, disjoint. So I'll have sum I equals 1 to N, probability of B intersect AI.
Do you need to have the B intersect there since it's kind of given since each A sub I is a partition of B?
Yeah, I need that B there. Excuse me, intersection there. Because I'm trying to get to Bayes' rule using the law of total probability.
So how is that different from writing probability of A sub I?
The union of A sub I.
So in your second thing there where you have the sum from I equals 1 to N, what's the difference between writing it as probability of B intersect A sub I and writing it as probability of A sub I?
Because I'm trying to get to Bayes' rule using this. In the sense, if I have multiple events, say A1, A2, etc., and B depends on A1, A2, all the way up to AN. Is there a way for us to write it so that we can get to base rule? It looks very trivial, but that's what I'm trying to do. So suppose we need to find probability of A given B.
And what?
Right? What would the numerator be? Probability of A intersects B divided by the probability of B.
This is the same.
Up
This is the same. It's the same B.
a what?
Like there's multiple B's.
It's the same B.
It's the same B.
Okay. Which A is it?
Uh,
A.
That's an arbitrary A. How about that?
It's A.
Union of those.
A sub X one.
Union of those.
Yeah.
So how can I write probability of A intersect B using a conditional probability? Multiplication, sure. So I need two things. I can't use A over B again. So what should we have here? So I want to write that using conditional probability, and Mary said multiplication. I agree. Two probabilities need to be multiplied. What are the two probabilities?
B given A.
Okay. Okay. A is the union of those. Divided by probability of B, we know that is equal to 1 to n. Probability of B intersect AI. I want to write B intersects AI using a conditional probability. And of course, I can't use A given B again. So how do we write that? Do you follow my question? I would like to write probability of B intersect AI using a conditional probability, but it shouldn't be that.
Probability of B. Are you asking me?
Yeah, because you just started, I thought you were about to
I
tell me.
want to write the summation symbol, it would just be probability of B, because that's what it equals.
Now, I want this part expressed in terms of a conditional probability.
Is that B given AI
B given AI
times probability of AI?
multiplied by the probability of AI. Okay, so what is the difference between probability of A by itself and probability of A given B? Think of what I mentioned last time. What is the difference between probability of A by itself against, probability of A given B?
You're given the help, you're told of the condition of B or the B sort of
Condition of B doing what?
you've been given that B is true.
I get it. So
Yeah.
But what does that given B mean? That's my question. I used a very specific word last time. Starts with the letter E, ends with the letter E. Evidence, right? Given an extra bit of evidence, what happens to A? And that is Bayes' rule. I'm going to write both of them here. So this is the same as saying A given B. I put the proportional sign because the denominator is a constant. So I could just call it, proportional if I get rid of that. So this is the new evidence. So we had an original probability. Now that I have the new evidence, that's going to change this probability. So in terms of Bayesian statistics, that is called the prior for A. This is the posterior for A. Prior probability by itself, if you bring in the evidence, it becomes the posterior probability. And that's called the likelihood. So the mantra for Bayesian statistics, the posterior probability is proportional to the likelihood multiplied by the prior probability. So all we are trying to say is that given if you bring in the information B, then the posterior probability is going to change, the prior probability is going to change, resulting in a posterior probability. Now, this could mean that probability could go up, go down, or remain the same. If it remains the same, then that new information that we've brought in has no meaning whatsoever. The denominator right here is what we call the normalization factor. If we extend this to not just probabilities, but to entire densities, we will talk about densities later, that will result in prior distributions and posterior distributions, using which we can calculate all sorts of probabilities in Bayesian statistics and methods. So this was done by a guy named, I think, George Bayes, or just Bayes something, hence the name Bayesian or Bayes rule. So suppose there's a box behind the curtain and we have 27 red dice, 30 blue ones and 42 white ones. Every die is 6-sided. So the probability that you get a 2 is 1/6. So Martin, I don't know why I picked that name, but Martin, is there a Martin in this class? No. So Martin is behind the curtain and he picks the die at random. So shuffle the box and pick one at random without looking and rolls it. He then yells out the number 2. Then he knows the color and the number also. our probability that we need to find is what is the probability that Martin rolled a blue die, in other words, he picked a blue die, given that you heard 2. Good. So we are looking for a conditional probability. So I'm keeping this here for a reason. Good. So what we're trying to find is probability of A given B. Given that you heard a 2, what is the probability that Martin rolled a blue die? So we know Bayes' rule states that probability of A given B is equal to probability of B given A multiplied by the probability of A divided by sum I equals 1 to n B given AI multiplied by probability of AI. Now let me ask you, well, what should that AI be? Now earlier in my explanation, I said AI, if you take the union, you get A, right? So what would each of those AI be? AI forms a partition. So think of the partition that I did. I said A1, A2, A3, and they're all disjoint. You put them all together, you get A. And what would AI be in this problem? Each kind of dice. And what is that entire A? All of them together, so that would be the box, right? So that box has the partition of each kind of dice. So the numerator would be probability that you get a 2, given that it is a blue die. Well, does it matter? That bit of information here. It's still 1/6. What is the probability that you pick, that Martin picked the blue die? 34 over 103. Was that Casey or Mary?
Macy.
Oh, Macy. No, wait. Mary, Casey, Macy. Wow.
Casey.
Who are you?
Sydney.
So who's Casey? Oh,
It's on the 30.
it's okay. Maximize it. So 34 divided by, so just to make sure, 6. Just the 6 here. 103. Yes. And I want you to find each of those probabilities and add them, or give me individual ones. In other words, what is the probability that we get to 2, given that you pick red dice? What is the probability you roll a 2, given that you get white, pick blue dice, given that you get a 2, probability if you get a 2, given that Martin rolled white dice, and so forth. So there are 3 possibilities. So we want to know those 3 possibilities, 3 different calculations, and I want their sum. Give me the individual ones first. Would this matter be given AI? Would it matter? It doesn't matter whether Martin rolls a red die, blue die, or a white die. It really doesn't matter. It's always going to be 1/6. Yes? Okay. Okay, what is the probability? There are three possibilities. A1, red, A2, blue, A3, white. So good. So what is the probability that you get a 2 given A1, which is red die? 1 out of 6. Multiplied by the probability that you get AI. Which would be picking a red die out of the total. Yes. Plus, when I is 2, probability that you get a 2, given you pick a blue die. What is that? 1 out of 6. And what is the probability of picking a blue die? It's 34. The last one. Okay. I guess I can erase this part now. Going to erase that part. We'll keep this just to make a point. So what is the sum? Well, what is the final answer? 44. So if you pull 1 over 6 out, you have 34 over 1 over 3. Here, and you'll just have 27 over 1 over 3 plus 34 over 1 over 3 plus 42 over 1 over 3. Yes. Well, 1 over 6 would get cancelled. The denominator is 1. So in chapter 3, we'll talk about a probability mass function. That's what it is. If you add all the probabilities in a probability mass function, you'll get 1. So denominator is 1, so you have 34 over 103. Good. Here is the question. The prior probability of getting, of rolling a blue die, right? Let's say I didn't even give you this information. I simply said roll a blue die. And what would that probability be? 34 over 1 over 3. Now I'm giving you this information, you heard it too, and I'm asking you the question, well, now that you heard it too, what is the probability that Martin rolled a blue die? And I get 34 over 1 over 3. My question to you is that bit of information of any use to you? No. In this problem, this did not give you any information in changing the prior probability. So if there is an effect, this prior probability posterior probability will change with respect to the prior probability and its likelihood, in which case bringing in this bit of evidence will change the probability of A occurring. That's why we call it the prior and the posterior. Prior would simply mean rolling a blue die. Posterior, given that you heard it too, what is the probability you rolled a blue die and In this case, it didn't change, so the information you brought in is useless. Good? Does that make sense? Okay. Write that down. We should be able to finish this. So consider the same example. Martin does the same thing. So we are going to consider the same example, but now you have 27 six-sided dice, 34 six-sided red dice, 34 eight-sided blue dice, and 42 12-sided white dice. Martin does what he did in the previous example, and we want to find the probability that Martin rolled a blue die, given that you heard a 2. Give it a try. So pretty much the same process, but what will change in this case? Well, we're saying probability that I want to be very specific. I'm looking for probability of A2. Right, which would be probability of A2. Yes. I didn't define A1, A2, A3 last time, so but I define it now. So since it is an 8-sided die, the probability that you get the 2 is 1 out of 8. The first one, red, 6-sided. The second, 8-sided. The last one, 12-sided. Yes. You put them all together in the calculator. What do you get? Is it 17 out of 49? As a decimal?
346 or 347. 347. Right. Got it for the first. Yeah, 347.
I'm going to put it as 0.3. I like 4 decimal places. Okay, now this is what I want you to do. I want you to find probability of A1 given B. We know probability of A2 given B already. Probability of A3 given B. So Martin yelled out a 2 already. Now, based on this problem, what do you think would be the most likely? Is it going to be the red dyes? Is it going to be the blue dye? Or is it going to be the white dye? Which is more likely when Martin yelled 2? You're saying red. Okay. Oh, you said red. Okay. The mask I couldn't hear. So let's find the probabilities and tell me what we get. So don't recompute the denominator time and time again. That's a normalization factor. This remains constant, which is why I put the proportional sign on it. So all we have to change in finding A1 given B is to have 1/6, 27 over 1/3. Denominator will be the same. And what did we get? 0.3673. Okay. Last one.
2857.
0.2857. If you add all of them, you should get 1. You better get 1. So that's called the conditional distribution. That's good enough. More specific, it's a conditional distribution of AI given B. Simply put, it is the posterior distribution. We are slowly moving into the concept of distribution, which is why I'm throwing these words in. So that's what I have. What is the prior for each of them? So the prior for A1 or blue dye, the prior for a blue dye is simply 34 divided by 1/3. Yes. So this didn't change much. If I simply wrote probability of A2, probability of A1, probability of A3. What are those decimal values? 0.26, 8.
0.2621.
Okay, that's 0.32.
301.
301.
301.
Okay. It's below 41 something.
4078.
Oh. Okay. What do we see from there to there? So all of these together would form the prior distribution. Right? If someone came up to you and asked, well, what color, what are the chances that Martin rolled the blue die? You'd probably say 33%. If you said, what are the chances that Martin rolled a red die? You would say 26.21%. And if it is a white die, you would say 40.78%. Right? Now that's without any information at all. Now we get a second bit of information, which is rolling or you hearing that 2. The moment you hear that 2, you know that the likelihood of 2 is going to be affected because of the number of sides that we have. Yes? So earlier I wrote the posterior is the product or is proportional to the product of likelihood and prior. So this prior distribution gets multiplied by the likelihood of getting a 2 in each of those 3 cases, and it changes the probabilities. So in this case, does conditioning change? Is conditioning worth it? Does it have, did the evidence have an effect on the probabilities? It certainly did. And we can say that the highest probability is with the red die. So the chances that he would have rolled the blue die is 34.69%, but which is the most likely die that he tossed or rolled, it would be a red die. Now here is the question. If I kept that as is, but I changed, instead of 42, I said 428, very great, at 4 times 2, 8. 428 12-sided white dice. Everything remains the same. And I asked you, given that you heard it too, which is the most likely one, what would your answer be? Huh?
Probably white.
Probably white? Right, and why is that?
There's just so many more of those.
Exactly. So this is where, frequency statistics and Bayesian statistics mingle. If you have more of something and you observe that time and time again, that is more likely. So if this increases, it tells us, okay, I've got the likelihood of getting a 2 from a white die is higher compared to getting it from a blue or a red die. So Martin must have picked a white die. Does that make sense? So that is the entire concept of Bayesian statistics. What information does the evidence bring in? Would the information change the prior probability of prior belief? Here, it got changed, and we have that. That's the posterior distribution.